Today I'm going to talk to you a little bit about percent composition and empirical and molecular formulas. But the first thing that we need to do is do a little bit of a review about what percents are. So a percentage is always the part that you're talking about divided by the total times 100%. And this may seem straightforward, and it is pretty straightforward, but I find that a lot of students don't remember that, and without that base knowledge, it's sometimes difficult to be able to calculate percentages in chemistry. All right, so just as a very basic example, if you have a slice of, or a piece of pizza, or a pizza that has 8 slices, and you eat 3 of them, what percentage of the pizza did you eat? So this is basically, we have one pizza, and we take 3 of them and put them on our plate and eat them, and there are 5 slices remaining. Okay, so we want to know the percentage that you ate. So that part that we're interested in is the part you ate, so that is 3. And then we want to divide that by the total. And that's not the total you took, it's not the total that's left, it's the total that you started with. So there were 8 slices to begin with, so it's 3 divided by 8, and then times 100%, and that gives us 37.5% of the pizza is what you ate. Right, now this leads right into mass percent, which we're going to use in chemistry. And mass percent is the mass of an element divided by the total mass of the compound times 100%. So again, this is just another percentage like we calculated before, we're just using compounds now. So we can calculate this in 2 different ways. The first way is if we're given experimental data, a problem tells us that there are X number of grams of nitrogen and X number of grams of compound. And we just take those 2 numbers and plug them into the equation above. The other way we can do it is using the empirical formula, and we're going to go through an example of both. All right, now let's do an example where we have the numbers given to us. So our mass percent is going to be the mass of the nitrogen that we're looking for. So we're looking for the mass percent of nitrogen. And the problem tells us we have 7.64 grams of nitrogen. And we want to divide that by the total, and so it tells us that we have 12.0 grams of N2O present, right? So that's our total mass of compound. So we want to do 7.64 divided by 12 times 100%, and that's going to give us 63.7%. Now we want to try this again using the empirical formula, which is given to us in the problem. So if we do that, then we're going to take the mass of the nitrogen on top, and the mass of the nitrogen in one formula unit of N2O is going to be 2 times the mass of nitrogen on the periodic table because it's N2O, right? So that's going to be 2 times 14.01. And then the mass on the bottom is going to be the total molar mass for that compound. So that's going to be 2 times the mass of nitrogen, which is 14.01, plus the mass of oxygen, which is 16. Okay, so when we add those together, we're going to get 28.02 for the top and 44.02 for the bottom. And then to calculate our percentage, we're going to divide those and multiply by 100%. And again, that's going to give us 63.7. So you can see that no matter which way you do the problem, you're going to get the same answer. It'll just be that in some problems, we have the experimental data to tell us how many grams there are, and then in other problems, we'll just have the formula and we'll need to figure it out on our own. Now we're going to move into empirical formulas, which we covered a little bit in class today with the Doser mass activity. So the empirical formula is just the lowest whole number ratio of the elements that are in a particular compound. This is a little bit different different than a molecular formula, because a molecular formula is for compounds that have covalent bonds, and it actually tells you how many things are bound together, whereas the empirical formula would be the reduced form. For ionic compounds, we always only report the empirical formula because we with a salt or something, we get a large lattice, and there could be thousands of sodium ions or chloride ions. So we always report the empirical formula for those. All right, so just as a couple of examples, let's do figure out what the empirical formula are for each of these. So C2H2, there are 2 carbons and 2 hydrogens. Both of those numbers can be divided by 2, so we can reduce that further to CH, right, which would be the empirical formula. Right, for part B, we have C5H10O5, and each of those numbers can be divided by 5, so we can reduce that to CH2, because 10 divided by 5 is 2O. All right, so there's 1 carbon, 1 oxygen, and 2 hydrogens when we reduce that. Right? NH3 has just one nitrogen and three hydrogens, so it can't be reduced any further. And so our empirical formula for this one is exactly the same as our molecular formula. Now, the empirical formula is a useful concept because it can tell us what ratio of the two elements we have, and it turns out that we can use experimental data to figure out the empirical formula. And we're actually going to do this in the lab next week. So for this example here, we have an iron compound that is used to purify water in water treatment plants. What is the empirical formula of the compound if experimental analysis shows that a sample of the compound contains 6.87 grams of iron and 13.1 grams of chlorine? So the first thing that we need to do, if we follow our steps that are up here, is to calculate the moles of each element. All right, because iron and chlorine don't weigh the same amount, so we need to know how many of each of them we have relative to each other. So we want to take 6.87 grams of iron, we'll do iron first, and multiply that times our conversion factor from grams to moles. So since we're starting with grams, we want to put grams in the bottom. If we look at our periodic table, we can see that 55.85 grams of iron is 1 mole of iron. Okay, and then when we do that division, we get 0.123 moles of iron. Okay, now we're going to do the same thing for chlorine. So we have 13.1 grams of chlorine, and again, we're going to use our conversion factor from the periodic table, and we can know that 1 mole of chlorine weighs 35.45 grams, which means that we have 0.3695 moles of chlorine. Okay, so when we have these two numbers, you can look at them maybe and see that we have about 3 times as much chlorine as iron in this case, but it's not always going to be obvious, and maybe this isn't even obvious to you. So to get whole numbers, which we can actually use in an empirical formula, we're going to divide by the smallest number of moles. That's step 2 up here. All right, so 0.123 is smaller than 0.3695, so we're going to divide both of them by 0.123. So that gives us 1 mole of iron and 3 moles of chlorine. So that's our ratio of these two elements in our compound. So our empirical formula is going to be FeCl3. Right, now the problem we just did gave us the masses for each of the elements, but what happens if the problem instead gives you percentages? So we just calculated mass percent earlier in this lesson, and a problem could give you those percentages as well. So for example, if you knew you had a compound that had carbon, hydrogen, and oxygen in it, then the problem could tell you that, for example, you have 59% carbon and 10% hydrogen, and to figure out the empirical formula. And in order to do that, you would have to know how many grams of each of them you have. But since they're percentages, we could just assume that we had a 100-gram sample. So that would mean if we have 59% carbon, then 59 grams of that would be carbon, and 10 grams of that would be hydrogen. And then we can also figure out from this problem, if we know the remainder must be oxygen, then that tells us that 31 grams of that sample would be oxygen. And then we can just go through the same procedure that we did on the last problem, converting to moles, then dividing by the smallest number of moles to get the ratio. Now the next question is, what happens if when you divide you don't get whole numbers? So let's say we divided and we get 1 and we get 2.5. All right, 2.5 is not a whole number, and it's not really clear whether we should make that 2 or whether we should make it 3. Okay, so what we need to do actually is find a way to multiply both of those numbers to get all whole numbers. So if we have 1 and we have 2.5, if we multiply both of those numbers by 2, then we get whole numbers. So if we multiply the first one, we'll get 2. And if we multiply 2.5 times 2, then we get 5. And so what this tells us is our ratio was actually a ratio of 2 to 5, not 1 to 2.5, because 2.5 is not a whole number. And so you can do this by multiplying by 3 if you get a third or if you get a 2/3, or by multiplying by 4 if you get a number close to 0.25. All right, and in a testing situation, I won't give you one that you would have to multiply by 5 because it's sort of a tough call if it's closer to 0.2 or 0.25. Now, as I mentioned earlier, we can relate empirical formulas and molecular formulas for compounds that are connected by covalent bonds, or so molecular compounds. All right, so if a molecule has an empirical formula of CH2O, what could possibly be the molecular formula for that compound? And so if we take a look at what we're given here, we know that the numbers have to be multiples of what's in our empirical formula. So CH2O and CH2O are the same, and so it's possible for the empirical formula and the molecular formula to be the same. So this one is possible. All right, C2H4O, so that means if we have one C in the empirical formula and 2 in this potential molecular formula, then all of our subscripts need to be multiplied by 2. So that would be C2H4O2, and this one doesn't have a 2 there, so that one cannot be a molecular formula. All right, but C2H4O2, which is what I just said, could be. All right, again, now we have C6H12O. So you can see our carbon is multiplied by 6, so our oxygen would also have to be, and it didn't change, so that one could not be. All right, and our ratio of carbon to hydrogen to oxygen is 1 to 2 to 1. So in this example where we have C3H3O3, that could not be the molecular formula because that's a ratio of 1 to 1 to 1. Okay, and then finally we have 5 to 10 to 5. And so that is also a ratio of 1 to 2 to 1. It's where all of our subscripts are multiplied by 5. Okay, and so now let's do an example where we look at how the molar mass is related to the empirical mass. So if we have a molecular formula for ribose of C5H10O5, then the empirical formula would have to be all of those numbers divided by 5 because that's the least common multiple. All right, so that would be CH2O as our empirical formula. All right, and our molar mass, we've calculated these a little bit in class, but we get that by doing 5 times the mass of carbon plus 10 times the mass of hydrogen plus 5 times the mass of oxygen. All right, and for our empirical mass, we would get that by doing carbon plus 2 times the mass of hydrogen plus the mass of oxygen. Now, if we multiply and add all of those numbers out, we get 50.13 grams per mole for the molar mass of ribose, and we get 30.03 grams per mole for the empirical mass. And one thing you might notice is that the factor that we use to get from the molecular formula to the empirical formula is 5, and the factor that would get us from the molar mass to the empirical mass is also 5. So if we did 30.03 times 5, we would get the molecular mass, which is 150. Okay, so that is the relationship between the molar mass and the empirical mass, which you can get by looking at the relationship between the molecular formula and the empirical formula. Now the last thing we're going to do is use that knowledge of the ratio of the empirical mass and the molar mass to find molecular formulas. So if we have vitamin C, which we know the empirical formula is C3H4O3, and we know that the molar mass is 176.12, then we can find the molecular formula. So the first thing that we need to do is find the empirical mass, and we get that by doing 3 times the mass of carbon plus 4 times the mass of hydrogen plus 3 times the mass of oxygen. And when we add all those together, we get 88.06 grams per mole. All right, and then we want to see what the ratio is between the molar mass and the empirical mass. So we're going to do 176.12 divided by our empirical mass, which is 88.06. And when we do that, we get 2. And that means that the molecular formula is 2 times the empirical formula. So we're going to take each of our subscripts and multiply them by 2. So that's going to give us C6H8O6 as our formula for vitamin C. All right, and so we're going to build on this in class, and we're even going to do a lab where we're going to figure out empirical formulas and do lots of practice problems.